Okay, class, hey, welcome back. Today we are going to dive into some deep water when it comes to atomic structure. Today we are going to talk about how atoms and the components of atoms arrange themselves, along with spending a majority of our time discussing how electrons behave within an atom and compounds. Our objective for today is to understand that atoms and molecules can be identified by their electron distribution and energy distribution. We can use this knowledge with the periodic trends to map out how atoms and compounds look like. In saying this, let's dive into some of these deep waters. Okay, so just to start off our simplistic stuff, we know that atoms are made up of three subatomic particles: protons, which are positively charged, neutrons, which are neutrally charged. Both the protons and neutrons make up the nucleus of an atom. This nucleus starts out nice and spherical in its form, but as we add more protons to it and neutrons to it, it starts looking more oblong and becoming more like a football or a rugby ball. Our last type of subatomic particle is our electrons, and we know these are negatively charged, and they are found outside the nucleus in what we call the electron cloud. We'll go more in depth on where these electron clouds are and how they exactly look in a minute. Atoms can gain or lose electrons and neutrons, but they cannot change the amount of protons they have. If an atom loses electrons, it then changes the atom's overall charge, making it an ion. Remember, anions are negative and cations are positively charged ions. If an atom loses neutron, then the atom changes its overall mass, which we call an isotope. We know from what we covered last year that electrons orient themselves within orbitals. These orbitals are located from the innermost to the outermost labeled as followed: S, P, D, and F. A s orbital can hold 2 electrons, one spinning in the positive direction, one spinning in the negative direction. The p orbital can hold 3 pairs of electrons, so 6 total of electrons spinning in opposite directions. And the d orbital can hold 5 pairs of electrons spinning in opposite directions. And finally, our f orbital can hold 7 pairs of electrons, so a total of 14 electrons spinning in opposite directions. A Fube's principle, I might have said that wrong, states that we must fill our electron orbitals from inside to out. Because some suborbitals can be found inside of other suborbitals, we must follow the following model: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, and 7p. Remember, we must be able to fully fill our electron orbital before moving on to the next level. So we must fully fill an s orbital before moving on to a p orbital, and so on. Last year we learned the long-handed way of writing these electron configurations. For example, calcium has 20 electrons. If we were asked to write the electron configuration for calcium, we would say 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. We can see with our larger atoms this can be a pain. In order to lessen the amount of writing, chemists have created a shorthanded way for writing electron configuration. Basically, they put the nearest noble gas that has a lower amount of electrons than the element we are looking at in brackets, and then write out the remaining electron configuration. For example, for calcium, we would write argon in parentheses, Ar, and then 4s2, because there's only 2 electrons left after argon's electron configuration. Let's do one more of these quick ones just to add an example for y'all. If we were needing to find the electron configuration for gold, which has 79 electrons, we would first look for the nearest noble gas that has lower or has less electrons than gold. This is going to be xenon. Xenon has 54 electrons, leaving us 25 more that we have to account for with the electron configuration. Once we do this, I find that my configuration is xenon in brackets 6s2, 4f14, 5d9. Now that's a lot easier than accounting for all 79 electrons. Now let's take these concepts a step farther. In order to start visualizing how atoms look and how electrons revolve around the nucleus, we must first realize that electrons act both as waves and particles, which in itself is kind of a hard concept to understand. Electrons exist around the nucleus as an excitation of particles or electrons in a standing wave, or in other words, a pattern. Just like our s orbital contains the least amount of electrons, it's going to be the easiest to visualize and understand. Our s orbital looks simply like a sphere around the nucleus. After we fill our s orbital, though, we move into our p orbitals. With our p orbitals, we got to understand that there are three ways p orbitals orient themselves. Okay, because we're talking about three-dimensional space, we have p orbitals that align themselves to the x-axis, p orbitals that align themselves to the y-axis, and p orbitals that align themselves to the z-axis. If I could summarize what these kind of look like, each one of these axes of orbitals looks kind of like two balloons tied together on this skinny end, with the fat end being opposite each other. The D and F orbitals are where we get a little bit crazy, and for the sake of our AP exam, I'm not going to go that far into explaining what they look like. But if some of you are curious, here are some examples to see what they look like. When we have multiple atoms interacting with one another, we can get orbital hybridization. Orbital hybridization is simply how orbitals minimize repulsive forces and orient themselves together when they bond to another atom. For example, an s and p orbital can hybridize. When an s orbital hybridizes with all three planes of the p orbitals, it is called an sp3 hybridization. We can have an sp2 hybridization or sp2 orbital when the s orbital bonds with or orients itself with two p orbitals or two p orbital planes. Finally, when the s orbital just orients itself with one plane of the p orbital, then we call this an sp hybridization. When asked, what is the sp hybridization of X compound, what do we do? Well, the first thing is we need to know the steric number. This number is simply the number of atoms bound to the central atom plus the number of lone electrons pairs present. When we add these two numbers together, if we get a sum of 4, that is going to be a sp3 hybridization. While if we add them together and get a 3, that's going to be an sp2 hybridization. And if we follow the trend, if we add the steric numbers together and get a number of 2, then it's going to be an sp hybridization. So let's do a few examples to show you what this might look like. Here's our first one. Let's find the hybridization of beryllium in BCl2. BCl2 looks like this when drawn out as a Lewis structure. If we were looking at the hybridization of the Be molecule, then we would add up how many atoms are bound to it, so the 2 chlorine, so 2 atoms bound to it, and then the electron pairs. Well, Be only has 2 binding sites, there's no other electrons with it, so it has no pairs, so there's 0 pairs left. So if I add 2 plus 0, this gives me a steric number of 2, which means my beryllium and my beryllium chloride, or BCl2, is an sp hybridization. Let's do another one. What is boron's hybridization in BF3? BF3's Lewis structure would look like so. Boron has 3 atoms attached to it and no lone electron pairs, so this would give me a steric number of 3. This means the boron in BF3 has a sp2 hybridization in this formula. Okay, for the sake of getting you an example of every type of sp hybridization, let's figure out the hybridization of nitrogen and ammonia. The Lewis structure for ammonia looks like so. We see that nitrogen has 3 atoms bound to it, which are your hydrogens, and 1 set of lone electron pairs. This gives me a steric number of 4. This means my nitrogen atom has a sp3 hybridization. Okay, that is most definitely enough for y'all today. Today we covered a lot of ground and reviewed subatomic particles, electron orbital and configurations. We also learned about how to visualize the different s and p orbitals along with how hybridization works. I hope you liked this video, and I hope it helped you out. Good luck in the classroom, and see you next time.